Hello dear students, this is Shakil and today we are going to discuss astrophysics as part of A2 revision. This topic is introduced this year from 2022 onwards, and this will be tested first time in exams coming up in May 2022. So as this topic is being included first time, so it's really important that all of you should know the direct knowledge very well, and then you can practice some questions at the end of this video lecture as well. So it's very important that you will be learning all the definitions and you'll be able to use all the formulas with all the correct SI units. If we discuss the content, the first thing is the standard candle. Standard candle is a method that was developed by the scientists to measure the distance of different distant galaxies and the stars from the Earth. They use the term luminosity, which is actually the power emitted by a star, and then the radiant flux intensity. Like this is the luminosity and radiant flux intensity. Luminosity is the total power emitted by a star from its surface, and radiant flux intensity is the power received on Earth per unit area per unit time from the star. So by knowing these two, they can find the distance of the galaxies or the star. The next interesting thing is stellar radii. So stellar radii is basically, again, using some laws in astrophysics, we can estimate the distance, we can estimate the radius of the star. Well, that's really interesting. Measuring the radius of the star while staying on the Earth. And then lastly, Hubble's law and Big Bang theory. I hope everyone is aware of Big Bang theory, the way how this universe was created, and then using the Doppler shift in the wavelengths, and then using Hubble's law, we can estimate, we can predict the age of the universe. Well, the first term is defining luminosity. Luminosity is actually the total power output of the radiation emitted by a star. So this is the standard definition. Then its SI unit is watt, and then the next thing is radiant flux intensity. So radiant flux intensity is the observed amount of intensity or the radiant power transmitted normally through a surface per unit area of the radiation measured on Earth. Well, simply speaking, we can say that the luminosity is the total radiation that leaves the star, and then the radiant flux intensity is the amount of radiation that reaches the Earth, or that is measured on the Earth. Well, by the time the radiation reaches Earth, the radiations keep on spreading out in the space. Therefore, only a very small fraction of luminosity or the power manages to reach on Earth. That's why the radiant flux intensity is always very, very smaller than the luminosity of the star. But it also depends upon the distance. If the distance of the Earth from the star or from the sun is very less, then of course less difference will be there between F and L. But if Earth is too far away from a star, then the bigger difference will be there between F and L. Okay, this picture sums up the things. Well, this is the star at the center, and as star don't know that which side is the Earth, actually star has to emit the radiation in all the sides. So when it emits the radiation, then the amount of the power that it emits on its surface is actually known as luminosity, which is energy per unit time. Luminosity is energy per unit time. It is energy per unit time, or it is actually power. That's why it is measured in watt. By the time as these radiation spreads out in all directions, of course the value of that luminosity or power keeps on decreasing because it is spreading away. And when some of those power or the intensity of the radiation reaches the Earth, of course that would be a very small fraction of what was emitted from the star. So the intensity of the radiation that we receive on the Earth is known as radiant flux intensity, F, and it is actually energy over time into area, right? So this is radiant flux intensity. Okay, now we have to look upon the relation between the luminosity and radiant flux intensity. So we know that as you move, as you can see from the light sources, that as you move away from the light source become fainter and fainter for you. Why? Because the light is spreading over a greater area. That's why less amount of light is reaching you. So the moment the light leaves the surface of the star, it begins to spread out uniformly through a spherical shell. Spherical, yeah, because it is being emitted in all directions. So the surface area of that sphere is 4 pi r square. So let's say if this is the light source, and then the light is being emitted in all directions like this. So you can see that now as light is traveling further away, then the radius of the sphere is increasing. So the radius of the sphere is r at all the points. So you can clearly see that as light is traveling further away from the star, the radius is increasing. Okay, so the radius r of the sphere is equal to the distance between the star and the earth. So this radius is actually the distance. Let's say earth is over here, so we can say that the distance of the earth from that star is r3. Okay, by the time the radiation reaches the earth, it has been spread over the area of 4 pi d square, and in this diagram it is 4 pi r3 square. Well, by using the inverse square law of the flux, we can state the relation between the radiant flux intensity, which is F, and the luminosity by the star, which is like F equals L over 4 pi d square, where F is the radiant flux intensity as observed on Earth, and it is measured in watt per meter square. L is the luminosity of the source, like the power that was emitted from the surface, the total power emitted by the star from its surface, and D is the distance between star and Earth. Well, we do make some assumption over here as well, and this assumption is that the power from the star radiates uniformly through space. Well, it means that, and one more thing is there is no object between star and Earth that can absorb it. Well, this equation also tells us that for a given star, the luminosity is constant and the radiant flux always follows the inverse square law. So the greater the radiant flux measured, it means the star is closer to the Earth, as it is clear from this diagram as well. Well, about the standard candles, this is actually a method. So a standard candle is defined as an astronomical object which has a known luminosity due to a characteristic quality possessed by that class of object. So this is the standard exam definition. This is the exam definition, right? So what is a standard candle? Well, actually it is a candle. Scientists develop a method while staying on the Earth using the candles to measure the distance of different galaxies, and in this the candle can be assumed as that star. So well, in astronomy, a standard candle is a source that has known luminosity, and luminosity is actually the total power output, and it is measured in watts, or we can also use solar luminosity, which is 1L naught equal 3.84 into 10 to the power 26 watt. So this is a standard thing which will be given in the data booklet as well. Well, measuring the distance using standard candles. Now we'll look upon how standard candle will be used to measure the distance of Earth from the star. So for distance, which are two laws to measure using parallax method. Parallax method is a method, we'll explain it later. Astronomers use standard candles. Well, this is a light source. This is a light source, let's say sun, and it is the source of luminosity. This is the Earth, and this is the distance. So we want to measure this distance, that how far away this star is from the Earth. So what we will do? So light sources which are further away appear fainter because light is spread out over a great area. If you know how luminous a source is, then you can estimate the distance, that how bright it will appear from the Earth. Well, the light which reaches the Earth has spread out over a sphere, and you know that the radius of the sphere, radius of that sphere is actually equal to distance to Earth. So what we do is the light has spread it to the sphere having surface area of 4 pi r square. So what we do is on Earth we have to measure the received power. We can measure that because we just have to use some instrument to measure the light intensity of light reaching us, and that is like F. So we can measure F. And then the next thing is the source luminosity, and then the area of the sphere. So what we do is that received power per unit area, we know this thing which is F, and then the source of luminosity or the luminosity. So we do know the luminosity as well through certain methods which we'll discuss later. So we know F and we know L, so using this we can measure this R. So the larger the distance, the smaller the power that we measure. Astronomers traditionally measure the received power per unit area in magnitudes, but like the watt per meter square is also a good unit for this. Well, the type of standard candle. There are two types of standard candles that we use to measure the distance of the galaxies. The first one is Cepheid variables, and the second one is 1A supernova. So these are the specific things. So Cepheid variables and 1A supernova are actually examples of the standard candles, and these are the objects which have known values of luminosities. Okay, so let's first look upon the Cepheid variables. The Cepheid variables are a special type of star with a luminosity which varies on regular cycle, like their luminosity keeps on changing, but their time period of changing the luminosity is linked with the amount of luminosity. So that scientists have developed a relation between the time in which the luminosity is changing to the value of the luminosity. So around 1908, Henrietta Leavitt discovered that the period of variability was closely linked to luminosity of the star. This is important. Period of variability closely linked to luminosity of the star. So if you time the variability of a Cepheid star or galaxy, then you can predict its luminosity. And if you know its luminosity and how bright it appears on Earth, like luminosity means L, and then how bright it appears on Earth means F, so then you can easily measure the distance using F equals L over 4 pi r square, where r is the distance, you have to measure that. So F is the radiant flux intensity you will measure on Earth. L is the luminosity, which is the characteristic feature in the Cepheid variables. You will measure that L as well, and using these two you can measure the distance. So Cepheids are used to measure the distance of galaxies out to about 30 megaparsec. It's again a unit. Not the SI unit, but the unit to measure the large distances. So Cepheids are what Edwin Hubble used to determine the distance of nebula. Nebula is actually the galaxies, and derive the Hubbles law. Well, the second one is type 1A supernova. Supernova occurs when the massive stars explode at the end of their life. You know, stars do have their age. Let's say the first one is nebula. Nebula is the mixture of dust and gases. It combines together to make a star, and this is known as a young star. And then as the nuclear fusion and fission going on, so young star goes into main sequence star, and then it goes to an old star, and then it goes to end of life. So when the star goes to end of life, it becomes very dense and heavier at its core. Like at its core, the very dense metals, let's say iron and some other very dense metals, are created over there because fusion keeps on happening. Initially, the star is, when it is nebula or young star, it is only having helium and hydrogen, but when the reaction keeps on happening, then more denser matter is being produced over there. So when the star reaches at end of the life cycle, what happens is that it explodes. So when it explodes, a lot of brightness is being produced. So that brightness is known as supernova, right? So supernova occurs when massive stars explode at end of their lives. A white dwarf and a red dwarf. So these are the two stars which are developed inside that star. So a white dwarf star in a binary pair with a red dwarf star steals mass from the red dwarf until it is too massive to support itself against the gravity anymore. So what happens is, when the star is at the end of the life cycle, then inside the star, two more stars are being created that are known as the binary pair. So one is the white dwarf star and other is the red dwarf star. So white dwarf star, what it do is it attracts the red dwarf star towards itself, because white dwarf is massive, so it attracts the red dwarf star, and then it collides, it collapses under its own gravity. When it collapses, what happens is that strong nuclear reactions happen and a very bright explosion is appeared, like the way it is shown in the diagram to the right. So that is known as the supernova. So because the collapse always happened to the same mass, this is interesting thing, that the star is going to collapse when its mass happens to be at one specific value, and this happens with all the stars at the same mass. So the luminosity of explosion is always same, because the same mass is going to explode, so same amount of light is going to be produced. So from this known luminosity we can estimate the distance. Okay, so supernova are very bright, often as bright as the whole, if you put whole the stars in the galaxies together, so their brightness would be less than the brightness of the supernova. And you can see them from the greater distances, like from the 10 billion parsecs. So the disadvantage of supernova is that they don't happen frequently around you. You have to spot them. Well, using standard candles as a distance indicator. Now we'll look upon that how we have discussed the Cepheid variable and the supernova, and what were those? Those were the standard candles. Standard candle is a thing which is having a known luminosity, like we know their luminosity value L. So now how we will use that to measure the distance. So, well, okay, so well, measuring the astronomical distances accurately is very difficult, yeah, because we can't use the direct distance measurement because things are very far away from the Earth. So for very distant object, what we do is we use standard candle method. So now, point number one, if the luminosity of the star is known, then the distance can be estimated based on how bright it appears from the Earth, like F. So astronomers measure the radiant flux intensity, which is F, of the electromagnetic radiation arriving at the Earth. This is point 1. And then since the luminosity is known, like through the standard candle method, so then they can use inverse square law of the flux to find the distance. So it is like this thing again. So like R square is L over 4 pi F, and then you can take the square root of it to measure the distance of star from that. Okay, each standard candle method can measure distance within a certain range, like the Cepheid variable and 1A supernova. They are used to measure the distance of the galaxies from for a set distance from the Earth. So what we can do is we can collaborate all the data in the measurement from each method, and then astronomer build a larger picture of the scale of the universe. So this is known as cosmic distance ladder. Like you cannot use one method, like you cannot use the Cepheid variable to measure distance of the whole universe or the galaxy from anywhere in the universe, or you cannot use 1A supernova to measure the distance of any galaxy from the Earth. It's actually for every set distance there are different methods. For shorter distance you will be using different method. For longer distance you will be using a relatively different method. Okay, now let's look upon this cosmic ladder now. The first thing is Hubble's law, which is D equals V over H naught. H naught is D is the distance, V is the speed of the galaxy, and H naught is the Hubble's constant. So the first thing is the distance. The first thing is which is very far away, this galaxy cluster, which is 10 power 10 light years. And what is light year? Light year is the distance that light travels in 1 year. Like the speed of light is 3 into 10 raised to the power 8, and in 1 year 365 days, and in each day 86,400 seconds. So you can multiply them. This distance in meter is equal to 1 light year. So we can define light year as the distance light travels in 1 year. Okay, so if you are measuring the distance, which is 10 raised to the power 10 light year, so you have to use type 1 supernova, because that is used to measure the distance of any galaxy or star around the place where supernova is happening. Then the second one is the nearby galaxies, which is 10 power 7 light years. So for that, we use Cepheid variable. So this was the first method in the standard candle, and this was the second method in the standard candle. So actually, for both of them, you use standard candle. Standard candle. For 10 to the power 10 light year, 10 to the power 7 light year, you use standard candle. And then in the Cepheid variable case, what you do is, this is the period, x-axis is the period, and this is the period of variability of their luminosity. So this is variability of luminosities. And along y-axis is the luminosity. So all these are actually the stars in nearby galaxies, and their periods are measured, and then on the basis of the period we can measure their luminosities. Well, for the main sequence fitting for the Milky Way, like Milky Way, you know, is our galaxy in which we are there. So this is the Milky Way galaxy, and we are somewhere like here in the form of this tiny red dot. So we are there. Like this is our solar system, the red dot, and inside the solar system, Earth is there. So if you want to measure the distance within the Milky Way, that is 10 to the power 5 light year expanded. So what we do is we rely on the surface temperature. So we measure the surface temperature of the stars, that is measured by Wien's displacement law, we'll study later. Then you can measure the relative apparent brightnesses or the luminosity. And for the nearby stars, which is nearby stars mean that, yeah, within the galaxy, so we use the parallax method. And then for within our solar system, like 10 to the power -4 light years, we can use radar sensing method or radar ranging method. Let's say the sun is emitting the radiation, 7 type of radiation. So on the Earth, a transmitter can be there that can receive the radiation coming from that, and then we can use that method to measure the distance of sun from the Earth. Okay, now the Wien's displacement law. This is very important law, very important law. You have to memorize its definition, the statement, and the equation as well. So Wien's displacement law relates the observed wavelength of light from a star to its surface temperature. So this is basically relation between the wavelength and the temperature. Observed wavelength, the wavelength that you will observe here on the Earth. So it defines like this. So it defines as the black body radiation curve for different temperature peaks at a wavelength which is inversely proportional to the temperature. So black body is one theoretic object which is which is the best radiator and the best absorber. So we can assume that stars are actually the black bodies because they emit all of their energy that they produce. So that's why they are black bodies. Actually, the black body here means stars. So the black body radiation curve, why it is curved? Because the star is emitting different type of radiation. Let's say sun is emitting 7 type of radiation, right? So if this is sun, so sun is emitting 1, 2, 3, 4, 5, 6, 7 type of radiations, and all the radiations have different wavelengths. That's why this is written as the black body radiation curve for different temperatures peaks at a wavelength which is inversely proportional to the temperature. So its equation is lambda maximum is inversely proportional to T. That's a common sense thing, that if its temperature increases, then the maximum wavelength that it emits decreases. And you know, frequency and wavelength are inversely proportional. So if temperature increases, wavelength decreases, and then frequency increases. It means more energy is being radiated. So lambda maximum is the maximum wavelength emitted by the star at its peak intensity. Well, a black body is the one which absorbs all the radiation fallen on it, and it's also a good emitter and does not reflect or transmit any radiation. So black body is actually a theoretic object. However, stars are the best approximation because they have to emit all the energy that they produce. So the radiation emitted from a black body has a characteristic spectrum that is determined by the temperature. So here is the diagram. Along y-axis is intensity. These are the intensity of the radiation as observed on the Earth, and this is the wavelength of the radiation. So we can see that as the temperature is high, so peak is happening at a relatively lesser wavelength here. And as temperature increasing, the peak is happening at a longer wavelength. So for 3000, it is happening here. So it means that as temperature decreases, so lambda maximum is the one at which this peak happens. Lambda maximum increases. Well, the full equation for the Mains law, which was like lambda maximum is inversely proportional to temperature. So lambda maximum equal to constant over temperature. So from here we can develop this. Lambda maximum into T is 2.9 into 10 to the power minus 3 meter Kelvin. This would be given in the data booklet as well. So lambda maximum is the peak wavelength of the star and T is the thermodynamic temperature at the surface of the star. And remember, this temperature will be in Kelvin and this is in meters. Okay, so the equation tells us that if the temperature is higher, then the shorter wavelength at the peak intensity is going to happen. So the hotter star appears to be white or blue and the cooler stars appear to be red or yellow. The greater the intensity of the radiation at each wavelength is happening. So let's look here. Color of the star. If it is blue, star is blue, it means its temperature would be greater than 33,000 Kelvin. If it is white or blue, it means 10,000 to 30,000. For white, it is 7,500 to 10,000. Yellow white, 6,000 to 7,500. For yellow, 5,000 to 6. Orange, 3,500 to 5,000. And for red, it is less than 3,500. Okay, Stephen Boltzmann law. This is second important law. Well, you know that a star's luminosity depends upon two things. One is, of course, its surface temperature, and the second one is radius, how big the star is. If the star is big, it will emit more radiation, and if its temperature is high, it will emit more radiation. So the relationship between the surface temperature and radius is developed by the Stephen Boltzmann. That's why it's known as Stephen Boltzmann law. This is the statement of the Stephen Boltzmann law. The total energy emitted by a black body per unit area per second is proportional to 4th power of absolute temperature of the body. It means the total energy emitted by a black body per unit area per unit time or per second is proportional to 4th power of the temperature. So then this E over A into T is actually, okay, so now we have to look for the luminosity. So luminosity, luminosity is energy over time. So this luminosity is energy over time. So we can say, okay, this is luminosity, and you can shift A to other side like this. And then you can introduce a constant to fit this. So what's the constant? The constant is this one. So we say that L is sigma T4. So this is the equation. Again, it will be given in the data booklet for the Stephen Boltzmann law, where L is the luminosity of the star, which is measured in watt. R is the radius of the star. R is the radius of the star, remember. And then sigma is the Stephen Boltzmann constant. Its value will be given in the data sheet. T is the surface temperature of the star. Well, how you will estimate the radius of the star? Well, the radius of star can be estimated. This is really interesting thing, and this is very important as well. The radius of the star. Well, what you have to do is you have to combine Stephen Boltzmann law and the Wien displacement law. So you combine both of them to find the radius of the star. Well, let's look upon the procedure. The first thing is, using Stephen Boltzmann law, you will find out the surface temperature of the star. How much is the temperature of the star? Then secondly, using the inverse square law of flux, you will find the luminosity of the star, right? So this is the second thing. And then using Stephen Boltzmann law, the stellar radius can be determined. Like, look upon here, the first thing is the inverse square law of flux. So you use inverse square law of flux. This is inverse square law of flux to measure the luminosity. Okay, because you know the you know the distance, you know the radiant flux intensity, so using that you can find L. And secondly, using the Wien's displacement law, what you use is lambda maximum T into T is 2.9 into 10 to the power minus 3. So what you can do is you can measure temperature from here because you already know the lambda maximum. And then the third thing is Stephen Boltzmann law. As you know L from 1, and as you know temperature from the 2, so you can measure this R, which is the stellar radii. Well, emission spectrum, this is important. We have already done that in quantum physics as well. In quantum physics, but we have to redo it here. So astronomers are very limited in how much to how much extent they can investigate the object in space. The only thing that they have is the light or the radiation coming from the star or galaxy. So one of these techniques involve the emission and absorption spectrum. So what they do is they use the light or radiation coming from the star, and then they made the spectrum, and they made two types of spectrum: emission spectrum and absorption spectrum. So elements in the star like the hydrogen, helium and other gases, predominantly like hydrogen and helium, absorb some of the emitted wavelengths. So therefore the characteristic lines are present when the spectrum is analyzed. So let's say if you use in the lab, if you measure if you make the regular hydrogen spectrum, so it appears to be in the form of absorption spectrum. So this is actually not absorption, this is the emission spectrum. So this is hydrogen emission spectrum in the lab. Okay, so now when the same spectrum is observed from a distant galaxy, all the waves seem to be shifted towards the red. You can see that the bottom spectrum is shifted towards the red. So when it shifts towards the red, then they can analyze about the distance. So when astronomers observe light from the distant galaxies, they observe difference in the spectral lines to the light coming from the sun, and the lines have the same characteristic pattern, meaning the element can still be easily identified. They just appear to be shifted slightly towards red or blue. The lines in the spectrum from the distant galaxies show an increase in wavelength, and the lines are moved or shifted towards the red end of the spectrum, which means that like the galaxy is moving away or it is far away from us. Okay, what is the redshift of the radiation? Well, we have to recall the Doppler's effect here. That Doppler effect is the apparent change in the wavelength or frequency of the radiation from a source due to its relative motion away or towards the observer. While on Earth, Doppler effect of sound can easily be observed when the sound waves move past an observer at a notable speed. In space, the Doppler effect of light can be observed when spectra of distant stars and galaxies are observed. This is known as like redshift and blue shift. So what is redshift? Redshift, if the object is moving away from the Earth, then whole of the spectrum coming from the being made from the radiation coming from that galaxy would be shifted towards the red end. Like in the previous slide we have done that. So that means that all the wavelengths are shifted towards the red end of the spectrum. It means the object is moving away from Earth. And if it is shifted towards the blue one, it means it is moving towards the Earth. So redshift is defined as the fractional increase in the wavelength due to source and observer receding from each other. Receding means moving away. So this is the equation, the Doppler equation that we will use here. So this is the Doppler equation. So delta lambda is the change in wavelength or the shift in wavelength divided by lambda, which is the wavelength emitted from the source, equals to delta f over f. Delta f is the shift in frequency, change in frequency, and f is the frequency emitted by the source, equals to v over c. V is the speed of recession, like what is the speed by which the object is moving away from you, and c is the speed of light in the vacuum. This is very, very important equation. Okay, now the last of the slides, it's an expanding universe. We are shifting towards the Big Bang theory. So after the discovery of Doppler's redshift, astronomers began to realize that almost all the galaxies in the universe are receding because they were just receiving the redshift in the spectrum. Redshift. So redshift means that object is moving away from you. So they realize that all the galaxies are moving away from each other. Okay. So this shows that the universe is expanding. The expansion stretches out the light waves as they travel through the space, shifting towards the red end. So, of course, when the galaxy is moving away and it is emitting some waves, so when the waves will reach us, the wavelength will be longer because the source is moving away. So that is redshift. So the more redshifted the light from a galaxy is, the faster the galaxy is moving away from the Earth. So you can see from here that this balloon is, when air is being exploded, is pumped in, then all these dots are, before you pump the air, the dots are very close, but when you shift blow the air, then all the dots are moving away from each other as well. And when the galaxies move away, they, like, if the galaxy is farther away from us, then it is traveling more faster, and if the galaxy is closer to us, it is moving slower. This is because of the gravity as well. If the galaxy is away, so it is under the less gravitational force due to other galaxies. That's why it is moving faster. So the expansion of the universe can be compared to the dots on the inflated balloon. As the balloon is inflated, the dots will move away from each other. So in the same way as the rubber stretches, when the balloon is inflated, space itself is stretching out between the galaxies. Just like the dots, the galaxies move away from each other. However, they themselves do not move. Well, Hubble's law and the Big Bang theory. This is the last topic and very important as well. So Edwin Hubble investigated the light spectra emitted from the large number of galaxies. So he used the redshift data to determine the recession velocities. Recession velocity is the velocity of movement of the galaxy relative to the Earth, relative to the Milky Way galaxy, and the standard candle method. So he used recession velocities and the standard candle method to determine the distances of the galaxies from us. So from these measurements, he formulated a relationship known as Hubble's law. This is a great work. This is really great. By living on the Earth, you can tell about the galaxy at the edge of this universe, that how far that is from us. Although that is the approximation, but yes, on a valid scientific logic. You know, science is all about logic. You can sit in your room and you can predict the diameter of moon, the radius of the Mars, the diameter of the galaxies. So this is really interesting. So Hubble's law states that the recession speed of the galaxies moving away from the Earth is proportional to their distance from the Earth. So the recession speed is proportional to distance. So if the galaxy is far away from the Earth, its recession velocity will be greater. So this is V equal H naught D, where H naught is the Hubble's law, and V is the galaxy's recession velocity in meter per second, and D is the distance between the galaxy and the Earth. So this equation tells us the farther away the galaxy, the faster is its recession velocity. Okay, now what they do is they plot the whole galaxies on a graph. So this is the distance of the galaxies from the Earth, and this is their recession velocities. So you can see that galaxies closer to Earth are moving away at slower speed. So let's say these one, and the gradient of this graph gives you Hubble's constant, because this is recession velocity and this is distance. So Hubble's law is V equal H naught D. So H naught is V over D, which is actually gradient of this graph. So more distant galaxies are moving away at faster speed. So you can see that the distance between these dots galaxies are more. It means they are moving at higher speed. And the galaxy cluster, which are very close to each other, they are moving at slower speeds. So the age of the universe. Well, if the galaxies are moving away from each other, then they must have started from some point at the same point in the past. If this is true, then the universe likely began in a very extremely hot and singular point, which subsequently exploded to make this universe. This idea is known as Big Bang theory. The redshift of the galaxies and the expansion of the universe are now some of the most prominent pieces of evidence that suggest that this theory is correct, actually, the Big Bang theory. The data from Hubble's law can be extrapolated back to the point where the universe was started, like the origin, and then which shows the beginning of the universe. Therefore, the age of the universe can be calculated like this. T naught is 1 over Hubble's constant. This is the fixed constant, fixed equation which you have just to memorize. Like T naught is 1 over H naught. So H naught is Hubble's constant, which is known. So the current approximated age is 13 to 14 billion years for this universe. So there is still some discussion about the exact age of the universe. Therefore, obtaining accurate measurement for the Hubble's constant is the top priority for the cosmologists. Like, it's still working on it, that whether this Hubble's constant is accurate or not, because he predicted it few hundred years ago. Okay, so this is actually the Big Bang theory. First, the universe was a singular point universe. Then it exploded, and then all the galaxies are moving away from each other. So thank you, students. This was the basic theory. Now some practice questions are included here, and you can practice them. You can just pause the video, and this is the question. Just read the statement and try to solve it, and then this is the solution. After solving it, you can compare your answer with the solution. This is the second question. You can just pause it without looking at the solution. You can solve it and then you can compare your answer. Same is over here. And well, same as this. This is the question. Just pause the video to solve it. And then this is the solution for that. Again, this is the question. Pause the video and solve this question. And then you can check your answer. Okay, so this was the last thing. Thank you, students. What I can do is I will be uploading extra practice sheet in link below. So I'll add a link with this video, which will be having some more practice questions for astrophysics. I hope you found this video useful, and you can watch it again and again, and you can make your own notes from it. I hope that would be a good help for you, and thank you so much. The next video will be for the thermal physics, which I'll be uploading soon.